So I couldn't think of another way to answer this question. And somehow in my head, I'm still half convinced about the answer that I have in head and the answer that Professor Holden gave. But if you recall what you did in your last assignment, assignment 5, what we're about to show strongly resembles what you had to write for one of the questions in that assignment. So we found the expected number of people in one of these groups. So now what we do, we suppose, okay, suppose that the claim is false. So we suppose that for all group of 7 consecutive chairs, you have at most 2 cider drinkers. So what is the expected number of cider drinker that you should get for one group of chair? Well, it should be less than 2. It should be less or equal to 2, right? So again, he might have done a small typo in his solution. But if you suppose that in all 7 groups of consecutive chairs, you have at most 2 cider drinkers, and the expected value of cider drinkers in one group of consecutive chairs should be less or equal to 2. You can have more than that. Right? In all groups, you have something at most 2. So how would your expected value be bigger than that? It cannot be. So suppose for all group of 7 consecutive chairs, you have at most 2 cider drinker. This would entail that the expected value of x is less or equal to 2, which contradicts part A. Or must such a group of 7 chairs containing at least 3 cider drinkers. So again, slightly confused about this question, why it's here, but that's the idea. So I think that was the last question that I did not prepare but put in here. So do you guys have any other questions that you want to look at?
So I'm guessing that you don't know what the final exam looks like for tomorrow, correct?
No, I have no idea what the actual final looks like. 6.31, yeah, I can do that. So that was the proof, right? The proof of the trick that I give, I think. So we can do that, yeah. Yeah, part B is just contradiction. The odd thing is that he put a low. No, it makes sense. Like that's how it's supposed to be solved, but it just should not be in that chapter. So maybe I'll just tell Michiel to why is this question here? It should be in some. It should probably be in chapter 6, to be honest, not chapter 7. Okay, so I think someone wants to do question 6.31. So let's do this one. It's a proof, and So it's a proof. We're proving a kind of a theorem. So let me scroll back up. I probably had it already. Okay, I need to take this and copy this. The annoying thing is they say, as in exercise 6.30, define an infinite matrix and use it to prove this. Why would you do that? You don't need an infinite matrices, but we can look at it if you want. So let me just share again. So here, so if you're curious, there is this identity that you can also prove. Consider the following matrix. We're going to, so the matrix that they talk about is an upper triangular matrix, meaning that this upper triangle above the diagonal is all zeros. And then what do you do? Then the first power of x that you look at is x, x squared, and 3, and so on. So here, obviously, we won't be using this matrix. At least I don't think so. But we'll have to define some upper triangular matrix. So what is the idea of using that matrix is you're going to compute the sum of all the elements by looking at two different things. The sum of each row added with each other, and the sum of each column added to each other. And that's what you're going to look at. So here, I'm wondering if you guys see the proof already. So here, instead of this matrix here of x squared, what should we be putting? So this is a matrix where we have x, a bunch of zeros, x squared followed by a bunch of zeros. Instead of this matrix, the idea is the same. But instead of using this matrix, what matrix will I be defining? So one, maybe I'll mention this. So following.
Can you switch the screen, please?
Yes, sorry. It's this screen, right? I'm in the right screen. Yes. Okay. So the trick, if you don't like to use a matrix, think about the following. So when I do the probability that x is greater or equal to k, or for example, the probability that x is greater or equal to 1, what does it look like? Well, if you break it down, this is equal to the probability that x is equal to 1 plus the probability that x is equal to 2 plus the probability that x is equal to 3 plus blah, 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 up to infinity, right? Okay, so how many times do you get probability of x is equal to 1 in this formula? Dumb question, but still is the question. So here I'm going to count. Oh, no. Just count the number of times. So here I'm going to count. Here, how many times do I have x is equal to 1? In this formula, how many times does x is equal to 1 happen? The probability that x is equal to 1 happens how many times? 1. Okay. So in this formula, it better happens once. Only once. And is this true? Yes. when I look at these bigger values, sorry, look at these bigger values, what happens? Here, I no longer start at this guy. So every other value don't have this factor. So as desired, this guy contributes exactly to this number of guys once. Now you do kind of the same thing for x is equal to 2. Well, x greater or equal to 2 is equal to the probability that x is equal to 2 plus the probability that x is equal to 3 plus the probability that x is equal to 4 and so on. And now, so I have one of these guys in the first term, one of these guys in the second term. Are these the only two contributions that we'll have for x is equal to 2? The answer is yes. Right? When I go to x greater or equal to 3, this disappears. So how many times in this summation did I get x is equal to 2? I got it exactly 2 times, which is exactly the same amount of times that I got it here. I got 2 times x is equal to 2. So that's the basic idea of this proof. It's you just say, well, the number of times, so you can say, in general, probability that x is greater or equal to how could I write this nicely? Yeah, so I can say maybe each probability x greater or equal, greater or equal to k contributes exactly once to the number times times the probability that x is equal to j for j less or equal to k, right? I think that makes sense. So what does that mean? If I put k is equal to 1, then this guy, the probability that x is greater or equal to 1 contributes exactly once to the number of times the probability that x is equal to 1 for j less than k. So did I switch the order around? I think I might have. So here, if I plug in 2, 2 contributes exactly once to the number of times x is equal to, oh, I should put, it's a greater, right? Smaller, greater or equal to k. Yeah, I did switch the order. So again, that is the core of the proof. It's this observation. You can use it with a matrix. You can do it with an infinite matrix if you want to, but really the idea is to just observe this. You observe that each probability like this contributes exactly once to the number of times this in the summation. Or maybe I can say exactly 1. It's poorly written, but I think you get the idea. So each probability like this contributes exactly or increments the number of times number times is accounted for in the summation sum k is equal to 1 to infinity of probability greater or equal to k. So first observation, what does that mean? It means that therefore the number of times probability that x is equal to j number of times that the probability x is equal to k occurs in this summation is what? So knowing this, what can I say about the number of times this happened and this in this summation? It's exactly this k times, right? How many times did this happen? Exactly k times. Right? Here I know that this happens exactly once. Why? Because all of these guys do not contribute to the problem. When I put a bigger value here, I lose this case here. Right? All the other cases will start at something bigger than 1. So the only time I got this case here was from this guy. What about x is equal to 2? How many times did I get this x is equal to 2? Only 2 times. Because when I go bigger than 2, I lose this as a case. Same thing for 3. I get 3 in 1, 2, and 3. And all the bigger values, when I switch this to 4 and bigger values, I lose the case x is equal to 3. So do you guys kind of see the idea, or does that not make sense, or am I speaking the void? Like, or just one yes, one no. If you don't see it, just tell me. But that's kind of the idea of the proof here. It's just,
I don't fully understand.
Okay, so again, here, how do you break down an at least? How are you used to break it down an at least?
By using all the values that's greater than the minimum value.
Exactly. So I'd look at if x is greater or equal to 1, then x is equal to 1 or 2 or 3. And what do I use here? I use this assumption. The assumption here that I'm using is that x is a random variable that only takes these values, only integer values. So that's why I can break it down into these cases. So if x is greater or equal to 1, then I have a bunch of cases, right? Now, when I'm showing that these two things are equal, one thing that I can do is count. So this here, in this summation, how many times do I have x is equal to 1? And I have it one time, right? When I put k is equal to 1, I get 1 times x is equal, the probability that x is equal to 1. So I have only one time this probability. So if what I'm trying to show, the idea of this proof is to show that, oh, what I can do is, so maybe I'll do it with the triangular matrix as an infinite matrix, and you'll see it maybe clearly. But what I'm trying to show that the contribution, or the number of times in this sum that I get x is equal to k, is still exactly k times. So these two things will be equal. Each contribution of these guys is exactly the same. It hasn't changed. So if you don't like this proof, the infinite matrix that they want you to consider is this one. They want you to consider the following matrix. Consider x is equal to 1, and then a bunch of zeros like this. That would be your first row. Then you consider, so you don't even have to write it like this if you don't want to. Then you consider probability that x is equal to 2, and you write it twice. So maybe for some notation purposes, I can't type purpose. Oh, I'm in French. That's fine. Purposes? Yes? Is that purposes? How you spell purposes? I think so, yes, okay. Damn you, French keyboard. Okay. So for notation purposes, we abbreviate the probability that x is greater or equal to k to just xk. Right? I don't even need a capital X. I could just write it like this. So the summation that I'm looking at is the sum of these small xk's. So what I'm going to write instead, just to make it clearer, so I just use, instead of writing probability that x is equal to 2, now I can just write x2. This is x2, and again, I'm looking at the following matrix. Then on the third row, I'm going to write this. And so on. So times and a bunch of times. And I do that for a bunch of zeros, right? And so on. So I keep doing that a while. So I do that for every power, or for every values of k. Okay, so what is this summation? Well, this summation is the row sum, right? When you add each row together, what do you get? So the sum of one row is equal to 2 times, so this one is 1 times x1. This one is 2 times x2. This time is 3 times x3. This time is 4 times x4. So looking at the row sum, looking at sum of each rows, what do we get? Looking at the sum of each row, we get it's exactly equal to k times xk, which is just equal to k times the probability that x is equal to k. So the sum of all the elements of this matrix is equal to the sum from k is equal to 1 to infinity of k times the probability that x is equal to k. Right? So what I did is I added every row. So I looked at the sum of each row, and then I add this sum together. So that will give me the total sum of all the elements added together. But there's another way that you could do this. And the other way is to look at the column sum. In the column sum, what do I get? So I get x1 plus x2 plus x3 plus x4, etc. But using the column sum, we get what? So the sum of the first column corresponds to x1 plus x2 plus x3 plus x4, and etc., which is the probability that x is equal to 1 plus the probability that x is equal to 2, so on. So what we get, looking at the sum of each rows, the kth row adds up to this. And I'll just write it nicely like this. Now, using this column sum, what do we get? We get that the kth column adds up to is, maybe I'll make it more obvious, is the sum from k, j is equal to k to infinity of the probability that x is equal to j. So on column 2, I start at 2. On column 3, I start at 3. On column 4, I start at 4. So on the column k, I start at k, and I add all of these probabilities, which is, by definition, the probability that x is greater or equal to k. So the sum of all the elements of this matrix is equal to the sum of these guys now. Sum from k is equal to 1 to infinity. These probabilities. That's it. So we counted the same thing in 2 different ways. That's it. So it's a cool proof. Okay. If you study past exams, it's not a bad idea, but do it with the purpose of just training yourself to solve questions quickly. So you should, in terms of, you don't want to start writing all the solutions for all the questions. So you want to write solutions until you're point to, okay, I know how to write things. Once you are confident that you know how to write things, start not to write things and just start breaking down problems. At least that's what I would do. So if you're confident about knowing how to write things, stop writing. Just look at problems and think in your head, do I know how to solve this? I think that will speed up your studying. So I hope at this point in your studying, you guys are starting to feel a bit comfortable. Okay, if I have a question, like I know kind of what I need to write.